What we're going to start off today is we're going to start off by labeling some of the parts of an atom. Now, I've got your note sheet pulled up, and the one you have online is already filled in, but what I'm going to do is go in and fill in this one and talk about it as we go. So, to kind of get us started, let's do some shapes in here. So, there are a couple of parts of the atom. We're going to talk about some of these. I'm going to draw some in here, and then we're going to label them. Oops. And there's another one here. Okay, so here's our atom. And over here we have a particle, part of the atom, that has a negative charge to it. Over here we have another particle. This one's actually in the nucleus of the atom, and it's got a positive charge. And then we have another particle inside of an atom that has a neutral charge. It doesn't have a charge to it at all. We'll talk about why it's there. That's the kind of symbol I use to represent that it has no charge. So negative charge, positive charge, and no charge. So what are these? What are these particles that we're talking about? Well, I think most of us know that this one is actually called an electron. And it has a negative charge. And then, of course, that means that these other two would be the proton up here, and of course the neutron. And so these are all the base components of an atom. So the proton and the neutron are sitting on the inside in the nucleus of the atom, whereas the electron is orbiting on the outside. If you think about it, how big is an atom? Well, they're really very tiny. There is a lot of things going on in here that would take a lot longer to go into. They're beyond the level of the course, but just to know that this electron is very small. Even compared to a proton, it's about 1,000 times smaller than a proton. And it's really just a packet of energy. There's really no matter there to it. But it's moving at such a high velocity around this circle. And you got to imagine around an atom, this is a very small circle. And it's moving almost the speed of light. So it's going extraordinarily fast around a very small circle. You can, yeah, if you've ever held on to something like, we used to do a bucket of water trick where we'd pour a bucket in water, or pour water into a bucket rather, and you grab the bucket and then you sling the bucket in a circle, like up over your head and around in a circle, and the water won't pull out of it. That's how we demonstrate that centrifugal force. But think about if you were to start speeding that bucket of water up faster and faster as you're slinging it around your arm. Eventually your arm would just fall off or shoot off because there'd be so much force. You don't have enough power to hold that bucket in. Now think about the electron as it's zooming around at the speed of light around this proton. How much force do you think it takes for this electron and proton to pull on each other in order to keep the electron from just zipping off? Well, the answer is a lot. It takes a lot of energy to hold that positive charge and that negative charge in towards each other. Matter of fact, there are 4 fundamental laws of nature. One is the gravity, one is electromagnetism, one is the strong nuclear force, and another is called the weak nuclear force. And this is an example, the force that holds a proton onto a neutron. Sorry, my little lines are not wanting to participate with me. Is a great example of that strong nuclear force because it takes a lot of energy to hold these two together. If there wasn't any motion, the electron would just reach over and touch the proton. They cancel each other out. But because it's constantly moving and zipping around, it doesn't actually ever get into the center. And there's a lot of empty space in here, but there's a lot of force holding this on. How much force? Well, we actually can go and split this in some chemical reactions, and energy is released. And usually that's reactions that give off a lot of, called exothermic reactions. They give off a lot of heat when we go through and we slice this apart. We break that bond. But with heavier atoms, with things like plutonium and uranium and rubidium and other things that are just big heavy metals that sound kind of scary, there's so many protons and so many electrons, hundreds of protons and hundreds of electrons, all crammed into this little bitty space. All the electrons are zipping around through different orbits trying to avoid each other. There's a lot of force that it takes to hold that atom and make it stay together. And when we split those, when we release the electrons from the protons, there's so much more force being released. And you probably guessed that, like during an atomic bomb, that's a lot of energy being released. And where's the energy coming from? We are severing the electrons from the protons, and we are releasing the energy. We're releasing the energy of this strong nuclear force. And we're doing it with so many atoms and so many electrons. It's obviously a very big force. We all know how big, powerful an atomic bomb can be. Even 60, 70 years ago, they were still very powerful. You can only imagine what they are like today. So then what's this neutron doing in here? What's its purpose? Well, as the electron orbits, it is pulling on this proton. So if the electron were to orbit and be over here, well, at that instant in time, it is pulling the proton in that direction. Well, then a split second later, it's over here, and it's pulling the proton in that direction. So as it orbits, it's constantly pulling on this proton, which makes this proton want to wobble. It wants to make it like zip around and move around inside the nucleus. Well, the problem with that is that's not good. When you've got one proton and one electron, it's not so bad. But what if you had like 56 protons? Or 104 protons, and they're all zipping and zagging and wanting to go towards an electron, it would just cause a destabilization of the atom, and the atom would literally just fall apart. But by adding neutrons, we're adding something that doesn't have a charge, but we're adding something that does have mass. So literally, they just act like anchors, and they keep the protons from jiggling around so much. It just adds stability to the atom. Now, in smaller elements like hydrogen and helium, we don't really see that many. Well, in hydrogen, we don't see any at all. I think there may be one in helium, or there's probably none at all. But we don't need that much stability in the atom because there's not that much chaos going on at the time. But the heavier an atom gets, or the further up it is in the periodic table, the more you'll start adding to it. And when you do, you have to add more neutrons to balance it out. We'll talk a little bit about. Let's talk about this thing called an atomic number. And so what is an atomic number? Well, an atomic number is literally just the number of protons that an atom has. Atoms are defined by their number of protons. That's what gives it the characteristics that it has. Why is gold gold? Why is lead lead? Why is oxygen oxygen? Well, it's all based on the number of protons. Okay. So that's kind of why the number of protons is important, and because oxygen is different than iron, and iron is different than lead, and lead is different than gold, and it's all because of the number of protons. That's the number that we give that really separates the atoms apart from each other. So on the periodic table, they're in the number of their atomic number, which is the number of protons that they have. Each one's going up. Hydrogen has 1, helium 2, lithium 3, and so on. So you'll probably know most of that. So we've given this little dude, we've given it 4 protons. So how many electrons would it need to balance out those four protons? How many electrons would it need? I think most of you probably got it right, and it's going to need 4. But there's a certain way that we draw them. Now, just to keep it simple, so I'm going to have them draw positive and negative, so I'm going to use a black dot on this. So there we go. There's 1 electron. The thing is, down here, there's going to be the second one. There's a reason why we put him down here. So imagine that this is the planet down here. These are our little protons in the middle. We've only got 2. We need to add 2 more. But look, this circle, this is what we call an orbital. It's where the electrons can be found orbiting around the nucleus. It's really small. We imagine if you had a bunch of space junk in space and orbiting our planet. Actually, we do have a bunch of space junk in space orbiting our planet. And when they put a bunch in the same orbit, there becomes a time where they could actually crash into each other, and that could cause problems and damage to the instruments themselves, or the spacecraft themselves, or the whatever we have up in orbit. And also it knocks them out of orbit, and that can cause problems like they may fling off into outer space, or they may come crashing back down to our planet. So what do? Instead of putting all of them in the same orbit, when it gets too crowded, we simply move them up to another orbital. And so the first 2, this first orbital can actually hold 2 electrons. The next orbital can hold 2 as well. Well, not just 2. It can hold those 2. It can hold up to 8. Okay, so 1, 2 in the first orbital, 3, 4, it would be 5, 6, 7, 8. Excuse me, 1, 2 here, then 3, 4, 5, 6, 7, 8, 9, and 10, because it can hold 8 in the outer and 2 in the inner. So these orbitals, we actually give them names. Write it over here. And we call this the s orbital, and it can hold 2 electrons. This is what we call the p orbital. It can hold 8 electrons. Now, there are more orbitals than just those two. Excuse me. There we go. Say there's another one out here. Another orbital. Yeah, that works. Gotta love paint. There's another orbital out there besides all that. There we go. That looked a little better. We give these names as well. Let's give this one a name, and we'll give that orbital a name. Just imagine these circles go all the way around, just more orbitals so they're further out. This is the S, the P, this one is the D orbital, and it can hold 8 as well. And this one over here would be the F orbital, and it can hold like up to 16, I do believe. So the SP, the D, and F. Now, for our purposes, we're just going to worry about these that are on the a little bit further on the inside. So the S can hold 2, the P can hold 8. So let's imagine that instead of having, instead of having 4 on the inside, once again, gotta love paint and me. All right, I'm just going to put a number in here to represent the electrons, or excuse me, the protons that we have. So let's put 10. So if there's 10 protons in the middle, how many electrons would it need? It would also need 10 positive charges, 10 negative charges to balance each other out. Well, where are they going to go? We've already got 4 of them on there for us. So let's get back to these colors. So we have 1, 2 in the S shell, and it can hold 2. So the third one has to go on the P orbital. So 3, 4, here would be 5, 6, 7, notice how I'm doubling them up, 8, 9, and just like that on here, 10. And if you notice, this one has a full outer shell, or full shell, and this one has a full shell as well. It's on the outside, so it has a full outer shell. It's going to be this full outer shell, or this lack of a full outer shell for some elements, that actually is going to make a difference on how they react. So imagine I just took one away. Imagine that we had only 9 in its full outer shell. All elements strive to have a full outer shell, and that's very important because that's what makes them reactive. How close they are to getting it full is what's going to make them more reactive. If they've only got, for example, this one has 7 in its outer shell, what's going to be easier? Gaining 1 electron to fill in the spot, or losing all 7 to get down to the next full outer shell? Well, the answer is it's going to be much easier for this one to want to gain an electron and have a full outer shell than it would be to lose 7. But what if I had a full outer shell here, and it had 1 up here in this outer shell? Ooh, that's a big electron. Let's say, what if I had 1 in this orbital? So this would have 11 total, right? 11 electrons, so therefore 11 protons. What would it be easier to do? To lose 1 to get back down to this one and have a full outer shell, or to gain 8 more? Well, this one would be much easier for it to lose 1. Whether or not they're going to gain or to gain electrons or lose electrons is going to really make a big difference on how these things react. And it's the basic start of physics and chemistry. We start getting anions and cations, which are just ions, charged particles. They don't have to have a different number of protons than neutrons, so they end up with a charge. It used to be protons and electrons, so they end up with a charge. And once we start getting that, we start seeing some interesting chemistry happening. So, okay, let's move on to the next part.